All right, so tonight's lecture, we're going to start with number bases. So number bases are a concept that you've been using your whole life, but you didn't really, most likely didn't explicitly call out. So let's quickly define what constitutes a number base and some properties, and then we'll go in details. Like for example, all number bases, under number bases, all numbers represent a value. So that seems like circular logic. Like what's the difference between a number and a value? So we'll go into that in a minute. Base or radix defines a range of digit values, and each position carries a weight, which is the power of the base. So just by reading the text here, it seems like a little fuzzy. It's hard, even looking at it, if I didn't know the context of it, seems like a little odd, like what does this mean? So let's start off with something really easy. What value is represented by the following number? So you see that number in front of you, 10. What value does that represent? Feel free to take yourself off mute. This is a participatory class.
10.
10, right? That's the easiest answer. And you would be absolutely correct if we were in a supermarket, or if you're at the gas station, or if you were in a restaurant. That's a number 10. Because in the context of how you use numbers, 10 represents the value 10, right? If you saw that, it's be 10. However, now I said context is important. Now, if we use a context that you are in a computer science class, talk about data representation. In that context, what do you think that number is going to be, or what the value is represented there?
1 and 0.
10 is
2.
Yeah, 2. It could be 2, right? So now, just by saying 2, now you start to see the distinction that, yeah, even though the number there is 10, it could be in a different value, right? Depending on the context. So that's the difference between a value and number, is that a number 10 written there can mean any type of value depending on what the number base is. So for example, I mentioned earlier that if you're in a supermarket, or you're at the gas station, or you're in a restaurant, the value is 10, because in everyday life, we use what's called base 10, or what's called decimal. So which means that every digit has 10 values, like 0 through 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10, that's what's called base 10. So under that type of condition, this is the value 10. However, if we were in a computer science class talking about data encoding, this might mean 2. But why is it 2? Because in binary, it's base 2. So now that we understand the distinction is that the number can represent any value depending on the number base. So when you don't know what the number base is, when there's ambiguity, then that's going to cause problems. So that begs the question, what's a number base? Well, we talked about base 10 and base 2, right? So those are the two most common number bases in computer science. Base 10 is what you use every day, and base 2, binary, is what's used to store data inside a computer. Because computers store information as zeros and ones, or in our case, remember we talked about the transistors from last class, is data stored as on and off. Either it's light bulb is turned on or turned off. So it has 2 states of information. So looking at that, we also have some other common numbers like base 8 and base 16. So these are all computer science bases. There's actually even base 64 within emails. So a lot of different number bases, but these are the most common ones. So quick definition of a base again is that each digit in a number has a range of values. So in base 16, each digit can have the value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F, which means there's 16 distinct values at each digit position. So now I just said the word digit position. So digit position means that when a number has more than one digit, then each position in the number carries a weight, which is a power of the base. So that's a wordful, or let's say a mouthful. So what does that mean? So that means that And the number 549, actually, let me just draw it out because it's easier to see as I'm drawing it out. So you see the context of what we're saying instead of just looking at the notes and got to figure out, hey, what are you talking about? So let's just bring this up. Okay, so we have a number, we start with number 549. Okay, so what that means is out of this digit is, oh, by the way, this is how you denote that's base 10. If we have any ambiguity, you put a subscript there. And this tells me that this whole number 549 is base 10. Okay, so the way to think of number bases is 9 would be times 10 to the 0. And this is 4 times 10 to the 1. And this number is 5 times 10 squared. Okay, so notice this. Each position is equal to this number base, right? So wherever the number base is, it's times that number base to the whatever power. So we have 0, 1, and 2, right? So each position, first one is 9 times 10 to the 0. The 4 is times 10 to the 1, and 5 is times 10 squared. If I have another number to the left of 5, it would be times 10 to the 3rd. So each position is multiplied by a power of the base. So that's what it means. Okay. And in this case, if we do it, guess what? This is very straightforward. 9 times 10 to the 0 is 9. 4 times 10 is 40. And 5 times 100 is 500. Okay. So this is just a way of showing what a number base is, or the powers associated with the number base. So what I just showed you is also the easiest way of getting the decimal value of any number base. Okay, so let's see what I mean. So we have a number 1010 base 2, right? I'm gonna copy that. Let's come here and let's paste it. Okay, so having this number, this means that this is 0 times 2 to the 0, right? Because the number base here is 2, so it's times 2. This is 1 times 2 to the 1. This is 0 times 2 to the squared. And this is 1 times 2 to the 3rd. All right, so once we do this, this will be 0 plus 2 plus 0 plus 8. So 8 plus 0 plus 2 plus 0, this gives me 10. My number base is 10. So this tells me that this number at the top has this value in base 10. All right, so that's, again, this is how you arrive at the base 10 value of any number. All right, let's do another one. Okay, now we're going to do an octal. 34 in base 8, get its value. So 34 base 8, this means that this digit is 4 times 8 to the 0, and this is 3 times 8 to the 1. So this would equal 4, and this would be 24. You add it together, 28. Okay. All right, let's do the next one. I think the next example is going to be a hex. Okay, so it's 13 base 16. So we want to get its value. This is 3 times 16 to the 0. This is 1 times 16 to the 1. So this ends up being 3. And this is 16. So the resulting is 19 base 10. All right. Is this very straightforward, hopefully?
Yes.
All right. Thank you. All right. So what I want to do now is give you guys a few minutes. I want you to work on these 4 problems. I'm going to copy this over. So convert each of these numbers to a decimal value. So the question is, using the number-based method, find the decimal value for each one of these numbers, because each one is in a different number base. But we want to find the decimal value of these numbers. Okay, so give you just give you like 3 minutes to work on it. Shouldn't be very hard. Okay, so let's do this together. All right, so the first problem, 1, 1, 1, 1. This is 1 times 2 to the 0. This is 1 times 2 to the 1. 1 times 2 squared. 1 times 2 to the 3rd. And 1 times 2 to the 4th, right? So this is 1, 2, 4, 8, and 16. So I add it all up. This should give me, say, 20, 28, 31, base 10. The next one, 0, 1, 0, 1. This is 1 times 2 to the 0, 0 times 2 to the 1, 1 times 2 squared, and 0 times 2 to the 3rd. So this would be 1, 0, 4, 0. So this is, you add it all up, this gives me 5, base 10. Okay, so that takes care of the first two. Now let's do the next two. So we have 132 in octal. This would be 2 times 8 to the 0, 3 times 8 to the 1, and 1 times 8 squared, right? So this is 2 plus 24 plus 8 times 8 is 64. You add it all up, and that gives you what, 80, 88, 89, 90. It's 10. And they have 123 and base 16. So this gives you 3 times 16 to the 0, 2 times 16 to the 1, and 1 times 16 squared. And this is 3 plus 16 times 2 is 32, plus 16 squared is 256. So 256 plus 32, that'd be 280, 288, 291. Okay. All right, so did anyone have difficulty doing this?
No.
Nope.
All right,
Yep,
fantastic.
all good.
All right, so now let's move on. All right, so now we want to focus on the binary, because now that you know how to get the value from any number base, that's good. But however, as I mentioned before, the two number bases that we'll be using the most is going to be decimal and binary. So it would help to be able to convert, quickly from binary to decimal and vice versa. Again, any little speed would help, especially if you're doing just say a problem on a test and speed is important. We want to be able to do it more quickly. So to do that, it helps to learn the powers of 2. So if you see the numbers here at the top, you have 1, 2, 4, 8, 16. Every number is multiplied by 2, right? And then you get the next number in the sequence. So you double the numbers. So number doubling, 1, 2, 4, 8, 16, 32, 64. You have 128, 256, 512, 1024. So this number sequence, outside of a computer science class, where have you seen this number sequence a lot? You see this in everyday life. Where have you seen this number sequence? Come on, guys. I want to make sure you guys recognize that.
RAM numbers.
Memory, right? RAM, exactly. Or if you have bought a iPhone or iPad or any electronic device that has any capacity for storage, you see this, right? This is a number sequence. So when you bought a iPhone, Apple is notorious for trying to make things friendly and naming things, right? That are very gimmicky. So why didn't they make an iPhone 100 or 150 or 200? Nope, they just went with 16, 32, 64, 128, because even though the device is nice, the underlying storage that it's based on is binary, right? So data, regardless whether it's a PC or Mac or whatever, or an iOS, ultimately it's still stored on top of memory, which is binary based. Hence, you see these powers of 2. That's why you see these numbers all over the place, is because when you store things into memory, memory is based on powers of 2. So you see these doubling. That's why you're going to see numbers like this. So you're not going to see numbers like 100 or 200 or 300. Okay. When you actually do see things like that on a hard drive, a lot of times it's rounded down. Okay. All right. So with that being said, what's a benefit of doing this? Is, let's just say that using the powers of 2, let's do the first one. Using the powers of 2 method, this is how we would be able to do one of these problems. Okay, so see the first problem there. So I start off with, I see 1, 0, 1, 0, 1, 0, 1, right? So I want to do this quickly. So the way to do it is do your powers of 2 very quickly. It's like 1, 2, 4, 8, 16, 32, 64, right? I just wrote that down very quickly. And then what happens is everywhere where there's a 1 in the number, I want to add that. Okay, so which means I want to add 64. Oops, hold on a second. 64 plus 16 plus 4 plus 1. So that just give me 80, 90, 95. Oops, is this, wait, not 95. This is 60, 70, 80, 85. So it's 85 base 10. Okay, so that's how you use your numbers of 2. Instead of, this is not dramatic. All it's really doing is saving you from writing out 1 times 2 to the 0, 1 times 2. So you don't have to write all that. You're skipping that part and just writing out the resulting of the multiplication. Okay, so that being said, I want you guys to spend a minute and do the next problem using this method. So the next problem is 1, 0, 1, 1, 0, 1. Okay, give you a minute, use these powers of 2 method and give me the result.
Professor,
Yes.
can I see the answer?
Oh, no, I just want people to exercise do this.
Oh, okay.
Okay, so I think that should be enough time. So again, following this method, this is what you should have done. 1, I don't even have to write out 2 because I know there's nothing there. It's a 0. So 1, 2, 4, 8, 16, 32, right? There's no need to write it. If it's 0, you know it's going to be 0. So add that together, and this is going to be 32 plus 8 is 40, 44, 45. And there you go. Okay, again, it's not like 10 times faster. All it is cutting through a step of unnecessary writing things out, because you're just skipping right to the point where you're just adding the powers of 2. All right, let's go back into the lecture slide and see what's next. Fractions. Okay, let's talk about fractions now. So speaking of these powers of 2, if I have a number 1, 1, 1, 1, dot 1, 1, 1, we know that this is times 2 to the 0. These are number bases. This position is times 2 to the 1. This position is times 2 squared. And this is times 2 to the third, right? These are number bases. So looking at this sequence of numbers, again, as computer scientists, right? Because you guys are not necessarily programmers. You're in the major's not, you're not getting a bachelor's degree in programming. You're getting a bachelor's degree in computer science. So that denotes they have a scientist part of you. So as a scientist using observations, you see the sequence of numbers. What do you think the base should be over here? What do you think the exponent should be following this sequence?
-1.
-1, exactly, and it is. It's -1. This is times 2 to the -2, and this is times 2 to the -3. Okay, so that's how fractions are handled. Is that if you look at this sequence, moving to the left, the exponent increases a number, but moving to the right, it decreases a number. Okay, so so multiplying this out, what does that give us? This gives us 1, this gives us 2, this gives me 4, this gives me 8, right? So starting with 8, 8 divided by 2 gives you 4, 4 divided by 2 gives you 2, 2 divided by 1 gives you, 2 divided by 2 gives you 1. So this is actually going to be 1/2. Okay, and this is, and you divide that in half, you get 1/4, and you get 1/8. All right, so you're looking at that, say, wait a second, how am I going to remember this? So here's a nice little visual. Does that make sense now? It looks like once you hit the 1, it just flips it around, and then it grows again in the denominator, right? See, the denominator doubles in size as it gets smaller. Do you see that? It looks sort of like you flip it around.
That's pretty cool.
Okay, so that is how fractions work. So with that being said, when you have an answer, you can't say 5 and 1/8, right? So understand that this is equivalent to 0.5. This is equivalent to 0.25, and this is equivalent to 0.125, if you had to write it out. All right? All right, so let's see. Let's come back into the lecture slides. Okay, so now let's go start doing things in the other direction. What if I start out with a decimal number and I want to convert it to a number base, any number, other number base other than 10? Just say I want two examples here. I have 35, I want to convert to binary, and I also want to do it to octal. So to convert decimal to any number base, you use a method called divide by n, or divide by number base. So if binary is 2, right? Base 2. So that means I want to divide by 2. So here's how you do it. So 35, I would divide it by 2, and I keep track of the remainder. All right. So 35 divided by 2 is going to give you 17 with a remainder of 1, right? Does everyone agree? 35 divided by 2 would be 17 with a remainder of 1. Okay, because 17 times 2 is 34, plus 1 is 35. So once I do that, I want to keep dividing by the number base. So 17 divided by 2 is going to give me 8 with a remainder of 1. 8 divided by 2 would give me 4 with a remainder of 0. 4 divided by 2 would give me 2 with a remainder of 0. 2 divided by 2 would give me 1 with a remainder of 0. And 1 divided by 2 would be 0 with a remainder of 1. Okay, so I just keep dividing and keep track of the remainder. Once the number gets down to 0, I take the remainders and I go from bottom up and I write it out. And this is 1, 0, 0, 0, 1, 1, base 2. And that's your binary. Okay, so 35, if I divide by 2 and keep track of the remainder, that will give me my binary number, the base 2 number. So does this method work with any number base? The answer is yes. Let's just say I start off 35 again. And I want to convert 35 to octal. So I divide by 8. Octal is an 8. So 35 divided by 8 would be 4, right? Because 8 times 4 is 32 with a remainder of 3. And then 4 divided by 8 would be 0 with a remainder of 4. So this is equal to 43 octal. Okay, does that make sense to everybody?
Yeah.
All right. So now I'm gonna give you guys an exercise. Oh, it looks like it's not typed up here, but we'll just give you a handwritten exercise. So I want you to convert the following number. Let's do 67. I want you to convert this to binary, and I want you to convert it to octal. Okay, so 67, I want you to convert that into binary and convert it to octal. So give you 5 minutes. Just make sure you know how to do it.
Professor, sorry, what was the method called? Divide something? What was it called?
Divide by the number base.
Oh, thank you.
Okay, so let's do this together. So 67. Since we want to convert to binary, it'll be divided by 2. Let's keep track of the remainder. So 62 divided by 7 is, 67 divided by 2 would be 33, right? 33 times 2 is 66. So that would give you a remainder of 1. 33 divided by 2 would be, let's see, 16 with a remainder of 1. 16 divided by 2 is 8 with a remainder of 0. 8 divided by 2 is 0, remainder. Okay, so 4 divided by 2 would give me remainder of 0, would be 2. 2 divided by 2 is 1 with remainder of 0. 1 divided by 2 is 0 with remainder of 1. All right, so this is from bottom up. This is 1, 0, 0, 0, 0, 1, 1, base 2. Okay, that's 67 in binary. All right, now for 67, I want to convert to octal. It's divide by 8. So 8 times 8, right, would give you 64 with a remainder of 3. And 8 divided by 8 again would be 1 with remainder of 0. And 1 divided by 8 would be 0 with remainder of 1. So from bottom up, it's 103 octal. Okay. Everyone good with this? Okay, I'm not hearing anything, so I'm assuming that's a yes. All right, now let's move on and take a look at octal conversions. All right, so with octals, you're not going to see in life very much. All right, this was useful back in the day when our data sizes were smaller and storage size were smaller, so it was meaningful. But now the data size are so much larger that octals aren't very useful. But however, you need to know that they exist, right? So this is one of those concepts that you need to know they exist, but in reality, you're not likely to see this in life again after this class. But here you go. So octals are numbers, base 8, where each digit has the value 0 through 7. And we want to be able to convert it into binary quickly, right? So how can we do that? And the answer is very easily. So we start with, I'm going to highlight it, from binary to, let me highlight this, binary to octal. You want to form groups of 3 bits, starting from the right. And you pad on the left with zeros if necessary to form a group of 3. Once you have that, then you convert each group of 3 into a octal digit. So let's look at this example. We want to convert that into octal, right? This binary number. So following the method that is described, you start off with creating groups of 3, starting from the right. So it's really simple. I come here, I say, okay, this is one group, this is another group, and this is another group. So I have these groups of 3 bits. All right. So what's the next step? The next step is to convert each of these groups into binary. And this is a nice little table that was provided. So eventually, after a few weeks, you'll memorize this, right? Because not that many. But for the time being, use this. This is a nice little table that you can refer to. So what we want to do here is saying, look at 0, 1, 1. What's 0, 1, 1? 0, 1, 1 is 3, right? So we say this is 3. 0, 1 again is 3. 1, 0, 1 is 5. And 1, 1, 0 is 6. And that's how we convert to octal. All right. So binary to octal is very quick. All you have to do is find groups of 3 and then convert those 3 bits into the corresponding octal number. All right. So I'm going to give you guys this exercise to do. So here are 2 numbers. I want you guys to do it. Okay, give you like a minute. I want you to do these two problems. Convert these binaries to octals.
Professor, I have a question.
Yes, go ahead.
So you don't, do we add all of them up after we divide them in three?
No.
And
No, that's the number.
Oh, okay.
6533 is the
Okay.
octal number.
All right, thank you.
Okay, so let's do this. All right, let's do this one. Notice that this I'm going to pad with a 0, right? Should make it 3 bits. So this number is 662 in octal. All right, this number is 665. So 566 octal. Okay. So once you know how to the method of groupings of 3, and then if you know the binary, then it's very, very quick to translate a binary number to any octal number. All right, so now let's go the other direction. What if now you have a binary and you want, I'm sorry, if you have an octal and you want to convert to binary. So the same concept. So we have 735 here. So what you want to do is take each digit and do the exact opposite. I'm going to take each octal digit now. I'm going to paste it over here. And you take the octal digit and you convert it into binary. So 5 would be 101, 3 would be 011, and 7 is 111. You put it all together and you have your binary. Okay, so again, you work backwards. You start off with the octals and you convert the octals to binary, and then you concatenate, put together, and you're done. All right, so let me give you this exercise now for this problem. Give you like 1 minute. It shouldn't be very hard now. Now that you know how to do it, this should be really quick. Convert this to binary. Okay. Okay, so let's do this. So 2 is 0, 1, 0. 3 is 0, 1, 1. 1 is 0, 0, 1. 5 is 1, 0, 1. And 4 is 1, 0, 0. So put all together, and that is your binary. Okay. All right, so any questions about octal to binary conversions?
Professor,
right.
how do you do the binary one? Can you repeat it?
Which one? From octal to binary?
So from octal to binary, yeah.
Well, just look at this diagram on the right. Each digit, you convert it to binary. Right?
Oh, okay. Let's do the yeah.
Yeah, that's it. You convert each digit to it's 3. You look at this chart here. Convert each digit to a 3-bit binary.
3-bit binary. Okay, okay, okay.
And put it
Oh,
together.
yeah.
Does that make sense?
Yeah, that's easy. Yeah.
Okay, yeah. Fantastic. All right, now let's move down to hex. So with hex, hexadecimal is a base 16, which means that each digit position has 16 distinct values. So if you look at this table for hexadecimal, it goes from 0, 1, 2, 3, 4, 5, all the way up to 9, and then it goes to A. So the letter A represents the value 10. So you might ask, why not just write 10 in there? Well, because we put 10 is 2 digits, right? 1 and 0. So we don't want that. We want a single digit to represent a value. So hence, after 9, A represents a value 10, B represents 11, C is 12, D is 13, E is 14, and F is 15. So these are the distinct values there. So you might also see number bases. Let's just say I have number 100, right? Oops, let me change the ink. 100, it can be subset 16, says base 16. You will always also see it written like this. Again, depending on which book you're reading or what side you're on. So they both mean the same thing. Base 16 or subscript H means hex. Yet another way of seeing it is you might also see it written like this. Let's see, what is it? Hold on. Let's see, what is it? I believe it's 0x 100, something like that. You're going to see like this in front of it. So that is yet another representation of the number. Okay, so they all mean the same thing. It's hex. So now with that being said, how do I translate that to binary? And the way to do it is to look at the number of bits. Notice that instead of 3, binary is 4 bits, because you need 4 bits to represent 16 values. So other than having 4 bits, the rules are almost identical. All right, so let's show you what I mean. So seeing this number, and hold on, let me copy the table over as well. All right, so the difference between this is a binary. So convert it to hex, it's groups of 4. So I'm come here and say, there's one group, here's another group. Okay, groups of 4. Other than that, look up the chart and see what 1011 is. 1011 is B. 0101 is 5, and 1101 is D. That's it. Okay, this process is almost identical. The only difference is with hex, you're doing 4 bits and not 3 bits. All right, so I'm giving you this exercise to work on. Convert these 2 numbers into hex. All right, give you a minute to do those 2 numbers. Okay, so let's do this together. This number is easy. Split. So the 0110 is 6, and 1011 is B. So this is B6 base 16. With this number, let's see, we have 1, and now I have to pad with a couple zeros here, right? To make sure. So now this is 6, this is 7, and this is 1. So 176 base 16. Okay. All right. Hopefully that was really easy. And now let's go the other direction. So the other direction is I start off with a hex and I want to convert it to binary. So just like before, I take each digit and convert it into not 3 bits, but now it's converted to 4 bits. Okay, so 5 would be 0101. 3 is 0011. and 7 is 0, 1, 1, 1. That's it. Okay, so each digit here corresponds to 4-bit binary. All right, give you guys one last exercise. Is give you this number. I want you to convert it into binary. So this is now a hex number, and I want you to convert it to binary. Okay, so let's do this together. So 2 would be 0, 0, 1, 0. 3 would be 0, 0, 1, 1. 1 is 0, 0, 0, 1. 5 is 0, 1, 0, 1. And 4 is 0, 1, 0, 0. So put it together. That's one very big binary number. Okay. All right. Does anyone have any questions on this? All right, let's go to our last lecture slide, is generalizations. All right, so we've been talking about binary and bits. So when someone says n bits, they're essentially referring to the number of bits that compose the number. And the bits are labeled from, let's just say this is x, 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 say 4 bits. This would be bit 0, this is 1, 2, 3, and then it just keeps incrementing to x2, whatever the n is, right? So if you have multiple bits, the least significant bit is the one on the right. That has the lowest number base, or the lowest power, right? So that's 0. And then each bit moving across is labeled 1, 2, 3, and so on. All right. So some quick things about these bits is that if you have a 4-bit number, it's composed of 4 binary bits, 0s and 1s. So the smallest value is 0, but looking at this table, but when all 4 bits are turned on, which is 1, 1, 1, that's the largest value you can represent. So using 4 bits, the smallest decimal value you can represent is 0, and the largest is 15. So now if I double the size of the bits, you know, when it's all set to 0, it's still 0, but when I have all 8 bits now turned on, the number is 255. So by doubling the number of bits, you know, I'm not doubling the amount of information, because I doubled the amount of information from 4 bits to 8 bits. I went from 16 values to 256 values. So each bit that you add, you double the amount of storage with a single bit that you add. So from 4 bits to 5 bits, I would double. But if I add 8 bits, it's times 2, times 2, times 2, times 2. So you're actually multiplying by exponentially, okay? So that's why with 8 bits, the value is 0 through 255, so you have a lot more information that can be stored there. All right, with that being said, any questions about number bases, about any of the top stuff we covered tonight?
Wait, Professor, I'm just, what is generalizations then?
Oh, no, that's generalization just means generalizing. It's just things that didn't fit under one of the other headings. I say, okay, this is just wrapping up about bits.
Oh, okay. Thank you.
Okay, so sorry, I didn't think of a better way of saying, well, this is just a whole bunch of additional stuff on add-on, but it didn't really fall into any topic. Okay, it could have been called addendum, right? That would be another just add-on. Okay, any other questions?
Professor,
Yes.
I'm just curious, will these recordings be up on Blackboard soon?
Yes, over the weekend.
Okay, thank you.
All right, anything else? Okay, if nothing else, then thank you guys, everybody. Thank you for a good first week of class. And we will meet again next Tuesday. All right, have a good
Professor,
weekend.
I
Yes.
had a question. So where are you posting this the class videos?
This should be on Blackboard under
Blackboard?
under the schedule and syllabus. There should be a date for each class, and then that's where you'll find the lecture notes along with the recordings over the weekend.
Okay, thank you.
All right.
Professor,
Yes.
next Tuesday is a Friday schedule, so we're
Huh?
meeting next time Thursday.
Oh, that's important. Okay, guys. Let me. I think this is super duper important, right? So if we have situations like this where